Okay, so today we're going to talk about Coulomb's law. Coulomb's law is a law that describes the interaction of charged particles. And in nature, there are charged particles, and these charged particles could either be plus or minus. And if the particles are similar in charge, so if they're plus plus or if they're minus minus, they will repel each other. While if the charges are not similar in charges, so if it's plus or minus, that means they will attract each other. So when Coulomb's law is first introduced, it's usually introduced in the scalar form. So it's written as F is equal to K, Q1, Q2 over R squared. Q1, Q2, that's the charge of the first particle and then the charge of the second particle. And R is the distance between the two particles. And K is just Coulomb's constant, so it's just a constant. And Q, the Q's are given in units of coulombs, and R is given in units of meters. So I'll just write that down real quick. So coulombs, then R is meters, and of course force is given in units of newtons. So this means that if we want to find the units of Coulomb's constant, we just pretty much have to know that we eventually just want newtons. So doing that, these Q's will make C squared on top, since they're multiplying each other, while this R squared is going to make meter squared on the bottom. So all we have to do is just do this. So that this cancels out with the M squared on the bottom here, and this cancels out with the C squared on the top here. And another way that Coulomb's constant is usually written is, sorry, let me give you the value before that. So it's 9 times 10 to the 9 Newton meters squared Coulomb squared. And another way that it's commonly written is 1 over 4 pi epsilon naught. And yeah, another constant shows up here. And what this constant is it pretty much just describes how well that a material lets electric charges flow through it. So in this case, since it's epsilon with a 0, so it's epsilon naught, that means that this is the constant for free space. And in this case, free space is the same as a vacuum and is the same as air. And this is the permittivity of free space. So there's also another constant called the relative permittivity, and it's given as this. And this gives a multiple of how strong another material is from free space. So for example, if we have 8 for the relative permittivity, we know that this material has 8 times the strength as free space. So for example, this material, let's call it material 1, and it has a relative permittivity of 8. We just plug that in and we just multiply it by free space. Okay, so just to illustrate how to use Coulomb's law, let's just do a quick example. So it's plus 5 Coulomb charge, and then a minus negative 2 Coulomb charge. Let's say the distance is like 3 meters or something. And then now we just have to plug it in. K, 5C, negative 2C over 3 meters squared. I won't do the math, but you just get the point. You just plug it in and then you get a value. And in order to tell whether these charges repel or attract, you just have to pay attention of the sign in front after you multiply it all out. Since these are all positive except for just one negative here, there's going to be a negative sign in front. And that means that these charges will attract each other since it's plus and minus. Okay. So another way that Coulomb's law is written is in the vector form. So F vector is equal to K scalar Q1, Q2, which are also both scalar, but then now another vector comes, which is R, and another vector on top as well. And these subscripts are here just to show what these forces are affecting. So for example, if we have particle 1, this 1, 2 means that the force that particle 1 feels due to particle 2. And if it was 2, 1, then it's just the force of what particle 2 feels with due to 1. So the best way to illustrate this is just to draw a coordinate system, because that's why vectors even arise, because of coordinate systems. So 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. All right, so let's just draw like let's just use the same 5 coulombs, and then another one that's negative 2 coulombs. And now we don't know the distance between them. And then if we start drawing vectors, we'll draw the position vector. So with respect to the origin here to this particle, we can find the vector value. So let's say it's 2x and then 4y, so 2, 4. And let's call this particle 1. And we'll do the same thing for particle 2. So 4x and then 2y. So then now what we need to do is just subtract vector 1. No, like subtract pretty much like this vector from this vector. So yeah, in this case, so if we do that, we just flip this vector around like this, and we add this vector. Now that it's flipped, we could just do normal vector addition. We just put the tail of this vector to the head of the first vector. And then after that, since it's just normal vector addition, we find the resultant vector, which is this purple vector, and it looks like this. So then we just put this vector onto charge 1. And then we could have also done this just by doing vector, like normal vector subtraction. So 2, 4 minus 4, 2. We get -2 and then 2. So yeah, that's pretty much what we got if we extended the coordinate system. So yeah, 2 to the left and then 2 up. And yeah, so then now all we have to do is find the magnitude, so the length of this, and then plug it into here. And the reason why we only want the length here and only the magnitude is because it's in absolute value bars. And then we cube that, and then we put the vector value into this here. So vector value is the magnitude and the direction. So then after we do that, we get something that looks like this. And I'll go through the steps on why we eventually get at the last thing. So we could separate this into squared, and then we just do this, R1, 2. So this is the same thing. These two things, this here is the same thing as the bottom, and then we just move this out like this. So what this eventually what this leads to is the unit vector r hat. And the unit vector is it's a vector that has a magnitude of 1 but points in the same direction as this purple vector. So the unit vector will look something like this. It just has a magnitude of 1 and then it points in the same direction though. So if you see from the scalar and then the vector, it's the same thing, except we just have direction now. And some of you might see that there is a mistake. Why is this vector pointing away when this is a plus charge and this is a minus? Shouldn't the vector be pointing towards it since they're attracting? That would be true, but everything gets solved once you plug in the numbers. So now if we plug in the numbers, it's k 5c and then -2c, and then we get r1, 2, sorry, that should be absolute value bar, squared, and then the unit vector here. So I won't actually find the length of this. It's just like 2 squared plus 2 squared and then square root all of that. That's the length. But just Pythagorean theorem. But then the way that this eventually solves it is because of this negative sign here. This negative sign here solves everything because it will flip the vector back around. So at the end, the negative sign will have the vector like this. Because once you multiply it all out, there's just one negative sign in front. And this negative sign could just be put with this unit vector. Yeah, and it'll just flip the unit vector around. Okay, yeah, so that is Coulomb's law, the scalar form and the vector form in a nutshell. Thank you.